Let's orient ourselves in our journey. Our current locus is Vignette 1, Mathematics, in episode 1 of the series. Next up is some basic topology, starting with metric spaces, which consists of a pair of objects, X and D. X is any set, and to keep things interesting, we will assume that X is non-empty, and D is the metric, also known as the distance function, is a function from the Cartesian product of X with itself to the set of real numbers. Just to remind ourselves, the Cartesian product of A and B is the set of all ordered pairs AB, with the first component of the pair taken from the left factor and the second component taken from the right factor of the Cartesian product. And defined thus, the ordered pair guarantees that the order is unambiguous. A distance function must satisfy 4 properties in order to be a metric, and that's next. In what is to follow, it will be convenient for us to think of X as a space and its elements as points in the space. And so, for points, all points F, G, and H in the space X, the positive semi-definiteness property states that the distance from F to G, any point F to any point G, is non-negative. The identity of indiscernibles point property states that if the distance from F to G is 0, then they are necessarily the same point. And conversely, going in the opposite direction, the distance from F to itself is 0. The symmetry property states that the distance from F to G is the same as the distance from G to F. And finally, the triangle inequality property states that the distance from F to G is less than or equal to the sum of the distances from F to a third point H and from H to G. Note, the third point H can be the same as F or G or neither. As we shall see time and time again, the triangle inequality is a very important tool in analysis. And luckily for us, we have already met the Cauchy-Schwarz inequality, using which we can prove the triangle inequality in any inner product space. And further luckily for us, these 4 properties of the distance function matches our everyday notion of distance. These 4 properties must be satisfied for a distance function to be a metric, and here is a consolidated view of what we just discussed. Only to summarize that a space, a set X endowed with a metric D is a metric space. And to check your understanding of a metric, I have given you here a few exercises. There are 7 distance functions, k, d1 through d7, and you are to check if each of them is a metric. D1, D2, D4, and D5 are pretty straightforward. D3 and D6 require a little work, and D7 in exercise 3 is the Euclidean distance. And this asterisk here means that I will provide a solution for it, information about which you can find in the description below. But if you would like to try your hand at it, then you can use the hint, use the Cauchy-Schwarz inequality as a hint. Definitions, results, oftentimes examples, and when we have a sufficient number of those, exercises. That will be our cadence. And so here is a definition and some results. The open set is going to be a crucial tool in our tool set. And an open ball is a particular type of open set and is defined thus. An open ball with center little x in metric space big X with radius r, a positive real number, equivalently the R neighborhood of a point x little x in metric space big X is defined as all those points y in X that are at a distance less than r from X. Diagrammatically, here you have metric space big X in blue and open ball B with center X and radius R in black. Note that while I have represented X, metric space X, as a subset of the plane, you should think of X as an abstract set, but not too abstract, since we have already given it some structure by associating metric D with it. And thus, you should think of B as an unspecified n-dimensional sphere whose boundary, whose surface is not included in its extent, which I have tried to indicate as white dots. Metric space X2 I have drawn with white dots, though it is not necessarily an open ball, but it is an open set, as we shall discover soon. Next, two simple claims on open balls. Claim 1.5, the union of all open balls centered at a point little x in metric space capital XD, D the metric, is the set X itself. Equation 7 is an equality of sets. How do we establish equality of sets? By showing mutual inclusion, meaning that we have to establish that the set on the left of the equality is included in the set on the right and vice versa. How do we establish inclusion? Let's say left inclusion. Well, for given x in X, let A be an arbitrary element in the union of open balls centered at X. If A belongs to this union of open balls, surely then it must belong to one of the open balls in the union, which means that there exists a positive real T such that A belongs to the open ball centered at X and radius T. If we write down the definition of the open ball centered at X with radius T, we have this set here, which reads like so. All those y's in X such that the distance from X to Y is less than T. If we focus our attention on the first part of the expression, all those y's in X. Therefore, this set is a subset of X. And so A belongs to a set which is a subset of X. Therefore, A belongs to X, which establishes left inclusion. For right inclusion, take any arbitrary element A of X and consider the open ball centered at X and radius dxa plus 1. I have used plus 1, but you could use any positive real in its place. A belongs to this open ball because A is less than the radius of the open ball, dxa plus 1. And this being an open ball is a subset, is a bona fide subset of the union of all open balls. So therefore, A belongs to the union of all open balls centered at X. And since we have established left inclusion and right inclusion, we have established the equality of these two sets in equation 7. Pictorially, here we have metric space X and point little x in metric space X. And I've drawn an open ball centered at X. As we draw open balls of larger radius centered at X, eventually we will engulf all of X. But wait, have we engulfed more than X? Have we gotten more than what we bargained for? Is our proof incorrect? O ye of little faith. Let's revisit the definition of the open ball centered at X. It is all those elements y in X. And so our definition filters out anything that is not in X. And so our proof is intact and abides. An examination of unions invariably leads to an examination of intersections, doesn't it? What is the intersection of all open balls centered at a point little x in a metric space capital X? The claim here is that it is a singleton little x in equation 8. Equation 8 is an equality of sets. And to establish it, we have to establish mutual inclusion. The right inclusion is trivial, so let's attempt that first. X is the only element in the singleton X, and for any positive real R, X belongs to the open ball centered at X with radius R because the distance from X to itself is 0, which is less than R. So since X belongs to all open balls centered at X belongs to the intersection of all open balls centered at X. For the left inclusion, let's take a small detour. I claim that whenever we need to prove an implication, antecedent P, consequent Q, we can equivalently prove the contrapositive. Not Q implies not P, taken by negating the antecedent and the consequent and swapping their position. Why? How? Well, let's take a look at the truth table for the implication. The antecedent takes two values, true and false, and so does the consequent. And so we get a combination, 4 different combinations, and the implication is false only when the antecedent is true and the consequent false. If we now look at the contrapositive, so column 5 is a negation of column 1 and column 4 is a negation of column 2. The contrapositive is false only when not Q is true and not P false. And if we examine these two columns in green, they are identical, which establishes the logical equivalence of the contrapositive with the implication. Armed with this knowledge, let's now attempt the left inclusion. We are to show that if an element belongs to the intersection of all open balls centered at X, it belongs to the singleton X. Equivalently, we can show, as we have established, that when an element does not belong to the singleton, it does not belong to the intersection. And so let's take an element, arbitrary element A in capital X, which is not equal to X, and surely A does not belong to the open ball centered at X and radius half the distance between X and A. So A lies outside the open ball centered at X and half the distance between X and A. And since A does not belong to this open ball, is this one open ball, it surely does not belong to the intersection. So we have established that whenever an element does not belong to the singleton, it does not belong to the intersection. And by the logical equivalence of an implication and its contrapositive, we have also established that whenever A belongs to the intersection, it belongs to the singleton, which means that A has to be equal to X. And since we have established left inclusion and right inclusion, we have established the equality of the two sets in equation 8. Pictorially, as we intersect the open balls centered at X, every single open ball is eliminated by an open ball of smaller radius. And eventually, we are left with just the discrete point X. For our larger enterprise, this insight of the equivalence of an implication with its contrapositive, and more generally with any statement and its contrapositive, is a conceptual jump that we will capture and codify towards our understanding of mathematical intelligence.